Okay, welcome all to the second day of our Midrasha. Let me start with a short announcement. Today we will have a lunch in a different place than this building. So what we're going to do is we're going to meet at 12:30 after the last talk. We will gather downstairs, and Imbal will guide us to the restaurant that we will have lunch. She also asked me to ask if there is any dietary restrictions, like gluten-free or any of those restrictions. If you have any of those, please let her know. So in the coffee break, come to us, and we take care of that. Okay. So then I think it's time to start with the scientific program again. So it's a pleasure to introduce Jan Fyodorov, who will speak about resonances and wave reflection from a disordered medium, nonlinear signal model approach.
Okay, first of all, I'm very grateful to the organizers for an opportunity to attend this nice meeting in this nice environment. I really enjoy and surely will keep enjoying it to the end of the week. You should not be put off if you are put off. Some of you by this title, which maybe sounds for some people technical. I'll try to be expository, and for probably half of my talk, I'll just try to explain what is this, maybe sounding less familiar for many of you, nonlinear sigma model approach to disordered medium. We will see, hopefully, some overlay, but from slightly different point of view frequently, with introductory lecture of Jonathan. And just warning that despite being for 20 years working in the Department of Mathematics, as it's conventional in the United Kingdom, approximately maybe 20% of people working in mathematical departments are from different backgrounds. I'm from theoretical physics, and it will be immediately clear in my way of thinking of the problems and presenting of them. Still, I hope that it will help to establish some common language. Okay, so let us start really. Okay, this is all. Okay, second part, more or less research part rather than expository, will be based on preprint done in collaboration with my colleagues Mikhail Skvortsov and Kostya Tikhonov. So one of subjects of this meeting is trying to understand just behavior of a quantum particle in a random environment. This is about Anderson localization, as majority of us know, and also partly about random matrices. So let us start with extremely low-level introduction. Let us just have a reference, just a classical reference, and consider just a piece of disordered medium, a cartoon. So it's just, you may think of some medium in a finite portion of, in general, d-dimensional space. I was not able to depict it in d dimensions in 2. So, and inside are these red spots of, I tried to put them of small but finite radius, and this is a cartoon for scattering centers. So suppose one just takes a classical particle, or it may be point particle or particle of some finite radius, and just sends it with fixed velocity in such a medium. So it will go freely until it scatters randomly from, hits some scattering center and then goes in a random direction. So it's obvious to everyone that it will eventually result in particle diffusing in this medium, and classically characterized by its behavior or its propagation by diffusion constant, which just by dimension argument but also by more refined arguments should be basically of the order of typical separation between these scattering centers, which standard name for it in physical literature is mean free path. and squared mean free path divided by characteristic time between collision, which is product of the velocity with typical separation, it's just v times tau. So this is classical diffusion constant, order of. Now, what should be correct or reasonable quantum analog of this to study quantum counterpart of such a behavior? And we are not surprised to see here just, since we are discussing a single particle motion, so let us consider the following Hamiltonian. It consists of two parts. So let us first discuss the first part to make it contact with what yesterday was presented. So yesterday, Hamiltonians basically were the form Laplacian plus random potential. So I ask you, okay, deliberately, just to show you how physicists think of this, keep at least for this slide, probably then I forget about dimension constants like Planck constant h, like mass. Then I will set probably in my further slides most of them to just 1. But here I just put them in order you may enjoy how physicists think of this. So the first, forget about this part for the moment, but I included it, and this shows some departure from yesterday's discussion, and this deliberate because it will play some role in what I'd like to describe. So first term, so this is a gradient operator, so its square will be Laplacian. Right up to a constant, it will be Laplacian. So this is what this is called kinetic energy. Operator describing kinetic energy of a single particle. Now, I included included second term here in the brackets which squared. Physicists call this combination long gradient. And this long gradient in physical jargon is just includes a part which is responsible for describing, if it exists, if it's non-zero, a magnetic field which pierces this sample. So this particle, if it's charged like an electron, it may move in a magnetic field. Magnetic field is basically a curl of magnetic field potential. And this potential just enters a quantum Hamiltonian in this way, just as addition to gradient term. Why it's useful and frequently important to keep it, I will explain maybe shortly later. And then this is basically just decorated kinetic energy, and second term is potential energy. And we also should add some boundary condition, for example, Dirichlet boundary condition, making this operator self-adjoint. Okay, so if we are interested in describing a situation which is quantum analog of this classical diffusion, it's natural to assume that potential V is random in space and short range correlated, and physicists, in the simplest case, physicists just think that it's zero range correlated. It's like delta correlated in space. Constant in front of this delta function, in fact, it's important to have in mind, this is the way how parameter tau, mean free time, describe time between typical time between collisions, enters this quantum problem. It really enters as a coefficient, this coefficient strength of the potential or strength of the fluctuations of the potential. Of course, I can include a constant part or a smooth part, but I think of this potential as just mean zero. So I only consider, it's also for simplicity, I consider it Gaussian for the purposes of this talk. So it's Gaussian, it's only described by its covariance, and covariance for simplicity one can take finite radius, but I prefer for simplicity to take just zero radius. So it's delta correlated. So in which limit, physical limit, we should expect some relation to classical problem. Obviously in semi-classical limit. And semi-classical limit here, in some moral sense, is the same as weak disorder limit. So basically, this limit corresponds to a situation when the wavelength associated with the particle, which is inverse of its wave number. should be much smaller than typical separation between scattering centers. This is weak disorder limit in this situation. And what I describe later on, these various approximations which I describe and which I put under the carpet, maybe discuss with those interested afterwards, they are all implicitly or explicitly assume weak disorder limit. Okay, so in this limit we hope to see some correspondence with classical diffusion. One can consider even further, okay, in some sense simplification, but just modification. One can consider a lattice analog of this Hamiltonian, in which sense, so basically let us consider some domain in ZD, in a lattice, in an integer lattice, and associate with each side in this, okay, finite volume part of the lattice, and we associate basically with every point or side or node on this lattice vertex, we associate potential, the diagonal part. So if one basically discretizes this Hamiltonian, one then notice that potential part will be just random diagonal of this matrix. So dimension of this matrix is just the number of sides in the portion of space I take for analog of my sample. Basically, all diagonal parts, they are basically made of, or after discretization of this kinetic operator. And one may ask how then this magnetic field shows itself. And it shows as phases which are accumulated along the links on these or edges of this graph which represents this lattice. So now it's clear why it's useful and sometimes even necessary to include effects of magnetic field, because our matrices without these phases, they basically, if you like, real symmetric. And random matrix analogs of them will be Gaussian, say, just by symmetry properties, just Gaussian orthogonal ensemble, or GOEs. If you'd like physically to have a system which will be described by so-called beta equal 2 situation, or Gaussian unitary ensemble as an analog, then it corresponds to strong enough magnetic flux or magnetic field piercing this system. And as technically, very frequently, maybe I won't remind it again and again, but at least once I should mention that in the framework which I'm going to describe, and frequently also in random matrix world, working with complex valued Hermitian matrices is easier technically. Conceptually, it's frequently similar, but results are nicer. Their techniques are more abundant to work with them. And it's not only because of, say, determinantal structure of usual random matrix ensembles, but it seems that this complex structure really makes it even simpler to think of, say, Anderson localization phenomena and all that. So, yes, please.
So, what is the angle bracket here?
Okay, thank you for asking. Angular brackets from now on will denote averaging over the distributions of a random potential, or if I will discuss some random matrix analogs of distributions of probability distributions of the matrices involved. So it's expectation. Angular bracket stands for expectation.
So it's not like the expectation against the Gibbs?
No, it's expectation. So temperature will be set to 0 in this. In order to preserve quantum coherence, the easiest way is to consider 0 temperature limit. Temperature is interesting to include, especially if you are dealing with multi-particle effects. Here, everything will be about single particle, which is still interesting and rich mathematical and physical problem. So, please.
What are the TXY?
TXYs are just off diagonal. If this is a matrix, For example, if it's just in the simple situation is one-dimensional matrix.
I'm trying to link it to your story with scatterers.
Okay.
TXY.
Okay, they are basically TXYs are less related to scatterers, but if you look to discretize, they will be related with discretization of Laplacian, of diagonal elements of Laplacian.
That's deterministic.
Deterministic.
Okay.
It,
TXY, I should say.
okay. Now, after formulating the model, I'm free to consider whatever I want, and if this is usual the way we do, right? And there are yes. But if you really start with this with random potential, they will be fully deterministic, and their phases will be also fully deterministic on every link, on every edge. But in so-called Wagner approach to Anderson localization, this is abandoned, and all parameters are considered to be random. And this is important, in fact, one of the important models. Okay, I will probably never discuss what I wanted to discuss and then, but still it's probably useful for majority of people.
What is the relation between the magnetic length scale and the mean free path?
It depends. It may be different. If it's really, you see, if you consider very strong magnetic fields, then this magnetic path will be small, but this is more about quantum Hall physics rather than, but for what I consider this opposite relation. So magnetic field will be strong enough to violate time reversal invariance and make this complex matrix, but small enough in order to avoid quantum Hall physics, if you insist on on this. Okay, so this, now, how one should understand, probably a little bit accelerate, but still not much. So how physicists think about the system and when and why they expect to see or not to see diffusion, or diffusion, say, arrested by interference. A very useful way of thinking was proposed by David Thouless, Nobel Prize winner in 2016. Who said that basically in this model there are two important, or at least two, in fact more, important energy scales. Or, okay, from the very beginning, for those who maybe not heard about quantum mechanics for a long time, but probably in this conference at least some idea of quantum mechanics should be present, I'd like to remind the most fundamental, at least in my mind, probably not in only my mind, principle of quantum mechanics, of uncertainty principle, which makes in correspondence between momenta and positions. So basically, momenta is something which you can estimate by the inverse of the position if you do not keep dimension of h bar, but h bar in fact divided by Planck constant divided by position. And in the same way, time and energy are always in similar relation. If you have time, then you immediately in quantum mechanics have a corresponding energy scale which is inverse of this time, or rather Planck constant divided by this time. So this is in the heart of the argument of Thouless, because Thouless said the following: we are dealing with system in a finite volume. So necessarily its energy levels, which are basically eigenvalues of the corresponding Hamiltonian, will be quantized. It means that there will be typical separation between them. If you consider given, say, scale in energy, then there will be a typical separation between them. And this separation is called typical energy level spacing. It's inversely proportional to the volume, obviously. Now, this sets one important typical quantum mechanical energy scale, and its inverse sets the time scale, which is called Heisenberg time in this problem. But also we have a diffusion. So there is, for a sample of overall length or typical size L, we consider in all dimension, I mean more or less the same L, there is a time of diffusing through the whole sample. It will be given by squared size divided by diffusion constant, just by diffusion law. Therefore, there is corresponding inverse of it, which is Thouless energy. So there are two possible situations. Either Thouless energy is much larger than mean level spacing. Then, in time domain, it means that diffusion happens much faster, much before system starts to realize that there is these discrete energy levels separated by delta. In this situation, it's basically one cannot hope to see, or all quantum effects will be only perturbative. The system will be practically classical. It will basically immediately ergodize on the energy surface, and basically it will be, in first approximation, classical diffusion. So this is what Thouless said. And this situation these days usually associated with what is called quantum chaos. So this is useful to think of it as a system in which diffusion happens very fast. And this is the fastest scale. And therefore, we expect that corresponding eigenfunctions will be spread randomly but uniformly through the whole volume. There will be no, it's not that important what is the special dimension of this situation. And no special structure. And basically there is a conjecture in physics that in this situation one can just replace actual Hamiltonian of a system with a big random matrix taken from, say, one of classical ensembles. This is so-called Baigos-Giannoni-Schmidt conjecture, which is still open in mathematics, but no sober physicist doubts that it's correct, provided qualifications when it's expected to be correct. It's very easy to give counterexample, but we understand why these counterexamples happen. Okay. So this system in physics literature is called zero-dimensional, because dimension does not play any role, basically. Okay, now consider the opposite case, when Thouless energy is much smaller than delta. This is opposite situation. One starts diffusing, but diffusion time is much longer than corresponding Heisenberg time, and therefore one immediately starts feeling that levels are discrete, and then interference is expected to play important role. And what is the most important single particle interference effect? This is Anderson localization, arrest of diffusion due to interference effect. So let us think now. So far I appeal to diffusion. And therefore, I should exclude from my consideration, and indeed I do, purely one-dimensional system like a chain with, say, scattering centers, or in discretized version, just one-dimensional lattice. I should exclude it. Why? Because it's relatively easy to show that in this situation, diffusion, at least when only nearest neighbors, these T's that Offer asked about, if they are only between nearest neighbors, one can show that there is no place for diffusion, basically. So in this situation, there is no diffusion. So when I speak about one dimension, I will have in mind what yesterday I think was called strips. So quasi-one-dimensional systems. So they are either can be thought of just informally as coupled one-dimensional system, coupled in transverse directions, also in this direction. Or basically, it's basically, if you consider it in continuous version, it's just a strip with scatterers inside, and which still allows diffusion on small scale, but diffusion can be basically localization will be only possible in one dimension. So it's of finite, but maybe even big, but finite this transverse direction, and long in one direction. So these systems I will call quasi-one dimension strips. So in this situation, it's easy to see what Thouless argument gives. It gives that there is a length scale at which two quantities. So if one just increases length, since delta then decays as inversely proportional to L, but this Thouless energy decays as squared L, there will be such L made of diffusion constant, where they just compare. And then Thouless predicts that this is exactly the scale at which interference starts, and if one considers length of this tube or strip longer than this psi, then if Anderson localization will take place and eigenfunctions will decay with characteristic state psi. Now, this argument, one can also see what this argument gives if it's taken for face value in higher dimension, but it should be in fact amended. It's too simple-minded. It's morally correct, but should be taken with some caution. But there is, physicists developed some framework, which I'm going to speak in the moment, which basically helps to give some quantitative understanding of what happens in higher dimensions, or at least conjecture what happens in higher dimensions. And answer is that in dimension larger than 3, there is a critical diffusion constant. Diffusion constant depends on the degree of disorder. So if the smaller is disorder, the larger is diffusion constant. So if one decreases diffusion constant, then in dimension larger than 3, there is a critical value beyond actually phase transition, beyond which one gets, below which in the value of diffusion constant one has localization, and above which wave functions are so-called extended. They are randomly but more or less uniformly fluctuating, covering the whole space. And in dimension 2 becomes marginal. Physicists still claim that there is a full localization in infinite two-dimensional sample, but localization length is not proportional to diffusion constant like we expected from Fowler's argument, but rather exponentially growing with diffusion constant. Okay, but what is this framework which allows to get this more refined picture? And this is exactly the main supposed to be an introduction finishing, but it's just continuing. But I hope that for the benefit of the audience, I need to go slowly through that. So how one can address how one can ask meaningfully in this framework of Hamiltonian the question whether particle diffuses or not. A natural object is to look at probability to start at one point and to end at another point in time t. So if it propagates diffusively, then it's analog of diffusion. If it behaves very differently, in particular if it decays exponentially with distance between r and r dash, we are in localized phase. So how formally write this object? I won't derive it for you, at least in front of you after we can discuss it. But basically this quantity is nothing else, can be written as a product of basically of the resolvent of the or matrix elements between special points r and r dash of resolvent of the corresponding Schrödinger operator. And resolvent needs to be regularized in order to be well defined. When we add imaginary part with this sign, with positive sign, physicists call this advanced resolvent or advanced green function. They like to call resolvents green functions. So it's by good reason. But this is basically element of the resolvent. If it's with minus sign here, it's called retarded. So, or maybe opposite. I never remember which sign correspond to advanced and which to retarded. But important thing that every interesting object in quantum mechanics, really interesting, will involve at least pair of these. One advanced and one retarded. And it's exactly seen here. It's a product of the two. Okay, so what I write here is a Fourier transform with respect to time variable of this probability. And it's written as an expectation, this envelope brackets, I remind you, expectation of random potential of product of two resolvents with different signs. This is very essential, of imaginary parts. But eventually, for this object, one needs to set this in the end of calculation, one needs to send this regularization eta to 0. Okay, so physicists proposed a very efficient computational framework which grasps a universal, it means features which are expected to be shared by large classes of models, not depending so much on microscopic details. And this framework is known as nonlinear sigma model, and I will try to describe to you now. It was introduced essentially in all important but one feature by Franz Wegner. And this important feature is the name super in brackets. So what Wegner introduced was matrix nonlinear sigma model, but nowadays we know that really correct theory is supermatrix. For those who never heard, supermatrices is basically generalization of usual matrices, but allowing some entries to be anti-commuting, or so-called Grassmann variables. So these objects can be used to formulate corresponding, basically, okay, this is called field theory, but it's just, I would say, mostly resembles some statistical mechanics model. So every object of this sort, but even more generally, every object involving simultaneously advanced and retarded function and expectation taken over all types of randomness inside the Hamiltonian, eventually in this framework is mapped onto model of interacting supermatrices. Now, what is supermatrices? I should specify their size. Their size is finite, and this is of course great advantage, because if they would be of the same size as original, say, lattice model, would be no gain. But here, really, in every lattice side, so we now it's easier to think about lattice version of the nonlinear sigma model. So we have lattice sides. To every side, we assign a 4 by 4, not that big, supermatrix. But 4 by 4 in the case when it corresponds to applied magnetic field, and 8 by 8 if there is no. You already see why I like to introduce magnetic field. Because to work with something 4 by 4 technically is much simpler than to work with something of size 8 by 8. But conceptually it's the same. So per lattice we have a 4 by 4 matrix now. And these matrices satisfy constraints. This constraint is just that this matrix, when squared, gives just identity matrix. And this is nonlinear constraint. And that's the name nonlinear sigma model comes from this constraint. Also, second constraint, that trace, or rather, there is generalization of trace for matrices involving anti-commuting variables. It's called supertrace. But all its properties are more or less the same as trace with some correct signs included. So you may think if you are unhappy with super, you can always, when you see S trace, you just think of trace of a matrix. You won't be much off. So these are traceless matrices. So they are squared one and traceless, but of course this still leaves a lot of degrees of freedom, which should be somehow parameterized. So every expectation of this sort will be some integral over these matrices attached to every lattice side. Pre-exponential term will of course depend on what you'd like to average, but exponential terms, or physicists like to call everything which is an exponential an action. So the action term, S of k, this is universal for all objects of this sort. And this consists of the following. So on the lattice, there is interaction between matrices belonging to neighboring sides on the lattice, with a constant which is morally proportional to diffusion constant on microscopic scale. And second term, just a trace of matrix Q with some fixed matrix lambda, the diagonal matrix containing ones and minus ones. And coefficient in front of it is exactly this regularizer eta combined with imaginary difference between energies involved here. So you see, here energies are different. So distance between them I call, or half distance, I call omega. So omega comes just basically always combined with this regularization. But it's also clear from here if you just substitute here. So frequently I may forget about omega, just only consider eta. Yes, please.
So why is the probability like not dependent on the energy level?
Okay, it depends. This constant depends implicitly on energy. Like diffusion depends basically, if you consider quantum analog of diffusion constant d, it will be, you see, classical diffusion constant proportional to velocity. So it's proportional to energy. So it grows with energy. So it's here. But up to this, it's universal. But of course, again, assumption was that we are in semi-classical regime. It imposes constraint. If you consider something close to ground state, to lowest energy, it's not correct. But I already mentioned that we are dealing only in this high energy. Yes, please.
Yeah, if I remember well, it's crucial here, right, that the random field be Gaussian.
Yes.
Just to be.
I said from the very beginning that everything which I consider here for should be Gaussian.
If anybody tries to perform the computations, right?
Okay, there are heuristic ways of also performing, showing the relevance of this for non-Gaussian potential and how to renormalize, but also for finite range potential, for example. But of course, cleanest and way which we can control something is what you say, is Gaussian. Whew. Okay. Okay, if you never will have a chance to know why this is still. Huh?
It's a small f.
Small f is any combination which involves both advanced and retarded green functions. Polynomial, yes, polynomial. Better to think of it as arbitrary long polynomial. In fact, I'm cheating here, but I don't like to discuss it. Okay, size of the matrix will depend on the number of in products here, in some situations. In the worst situation, it will be related with the number of in products. If you have really only 2, it will be 4, as I said. So now the statement is correct.
How does the F appear on the right?
Huh?
How does the F appear on the right?
F, this F,
No, the other F.
this F.
Yes.
This I will say, consider arbitrary more or less polynomial in both quantities. Then it will be mapped onto some polynomial in entries of matrix Q. But different polynomial. But rule is known. Rule how to transform one to other is known. Okay, so how physicists think about derivation of this? Physicists think in the following way. The easiest physical way of arrive to this, and I think it's more or less like Yefetov, maybe not Wegener, maybe Wegener himself, arrive to this is the following way. Hopefully you remember about these grains or zero-dimensional models that I introduced. And they are described conjecturally, but correctly, by single random matrix. Now, think of a lattice consisting of different realizations of the same, I would say, ensemble of random matrices, or just granular of random shapes, but macroscopically the same, but microscopically they are different. First, switch off any contacts between them. Then, this is really a mathematical statement. One can map it onto this nonlinear sigma model with a single matrix Q. Because this is like a single site on this lattice. And this is now really rigorous. Single matrix Q. But then, allow these T's or hoppings or tunneling or whatever between neighboring sites. One can show then that interaction alpha appears from that. And then one gets interaction between, white gets only interaction between nearest neighbors, one can argue. But this is basically the way how physicists arrive to that. The easiest, okay, one can really give a mathematical meaning to it to consider so-called matrices made of blocks. This is so-called Wegener model. So Wegener derived to this nonlinear sigma model from that. And there you can really make it under control to some extent. But this is how one thinks of it. Now, remark is appropriate. So I showed to you really latest version, because the latest version is really the easiest to derive. But then after that, you may consider back making a continuous limit from latest version. It's clear. Considers lattice constant and length of edge shrinking and scaling basically other quantities involved in order to get finite limit. And then what one gets, for example, in dimension 1, one gets such a version of nonlinear sigma model. So instead of sum, you get integral. Instead of interaction between nearest neighbor, you have a gradient of Q. And so this is a type of action you should deal with. And then in this limit, really you see that coefficient, it was alpha, but in front of gradient is really proportional to classical diffusion constant. So you see contact with diffusion. Another way to derive at least this version, one-dimensional version, rigorously, is to consider a model of random matrices which have all entries random, but concentrated in some band around main diagonal. Not only just finite band, but you need to consider this band to be parametrically big and exploit this parameter, but still much smaller than the size of the matrix. So it's double limit. You consider size of the matrix to infinity, parameter b to infinity, and ratio of the two in some powers fixed. And then you can arrive to this type of nonlinear, exactly to this nonlinear sigma model. This was done at the level of theoretical physics in our old series of papers with Sasha Mirlin, and in recent years it was absolutely rigorously done by Tanya and Masha Sherbina. So we are on good ground here. Yes. Now, defined this nonlinear sigma model, I should mention one important object which was introduced by Martin Zirnbauer, who unfortunately was not able to come to participate in this meeting, as I was told. So he won't be able to criticize me for this presentation. But I'm not happy about it. I would prefer lively exchange. He introduced a really important object. He said the following: let us take this action of nonlinear sigma model, forget completely about pre-exponential terms, set them 1, and take one side of the lattice, nail Q matrix to some value, because Q matrix lives in some space, so fix this realization of Q matrix in a given site, and integrate over all other Q matrices. I mean, in principle. To do it in practice is, of course, a hard job, but let us define such object when you integrate this S over all matrices apart from fixed one. Then, obviously, you get a function which, not Martin himself, but I believe it's Sasha and myself called it, or the parameter. But it was really introduced by Martin, and with good reason we called it order parameter function. Because this function now, now it turns out that in the situation which I discussed, when underlying symmetry is time reversal symmetry of the problem is broken by applied magnetic field, when we deal with only 4x4 matrices, not 8x8, then it turns out that the corresponding left-hand side depends only on two real variables. And this is very nice. Okay, it depends on two real variables. One is called compact, and you can think of it as cosine. It lives between -1 and 1. And second is cosh. It's a hyperbolic really thing. It lives in 1 infinity, and in fact geometrically it parameter Q live on a union of a sphere and hyperboloid basically, dressed with anti-commuting variables. But its part which usual variables lives on these 10 minutes. Okay, fine. So this object really its dependence on lambda 1 changes drastically in two phases. This Martin showed that in one phase, where we expect localization, this function in the limit when one sends this regularizer eta, imaginary part of resolvent, if one sends it to 0, first of all, the limit eta to 0 and volume to infinity, thermodynamic limit, they commute, and the result is that y becomes constant, just independent of its argument. And this is one phase. In the second phase, this function retains non-trivial dependence on its argument, and this will correspond to diffusive phase. And one can show that basically in that second phase, that object that I started with, this probability start from one point and go to the other point, will be given by diffusion form in some range of parameters. At the level of this nonlinear sigma model. This is not a rigorous statement. Really, to make it rigorous will be extremely interesting, but I bet my life, it's correct statement. no one doubt. Okay, again, with qualifications. As always, as all correct statements. There are situations when this statement is correct. Now let us change. I have only 10 minutes left, maybe 8 minutes left. So now really I'd like to change perspective. So in the introductory lecture, it was mentioned that basically this is all about transport. What means transport? Transport means that we add particle here and we follow it and see how it goes elsewhere. But how to add a particle? The only physical way, and there is no any other way, is to have a system and to attach to it infinite dimensional, I don't know, not dimensional, some wire or waveguide or something of infinite length, and then send a particle through it, and then it will, from infinity, it will arrive here, will participate in the life of this system, and then eventually will go back. And this is the only physical way to study how it behaves. But this is nothing else, a scattering problem. And now, unfortunately, I have to accelerate, but there is a very nice framework. I just flash it. It goes back to Weidenmüller, Verbarschot, and again Martin Zirbauer. They worked that days in Heidelberg, so it's called Heidelberg approach. There is a way to, if one knows a Hamiltonian describing random media and attach to it a waveguide supporting many propagating modes without any disorder, so there is no anything disordered here. It's just a tube, empty tube which supports propagating waves. Then there is then the problem becomes scattering problem, and scattering matrix S is a matrix which relates amplitudes of waves which go this direction and which are reflected. And it's known how to write it in terms of the Hamiltonian. One basically again should use a resolvent of this Hamiltonian and sandwich it between two different vectors, and these vectors basically encapsulate boundary conditions between this waveguide and this random system. In this way, one gets access to scattering matrix. And scattering matrix also has a different representation, which by algebra can be reduced from that resolvent. And basically, it can be written as a resolvent of non-self-adjoint or non-Hermitian operator, which is obtained by deformation of an operator, which describes a system which had a finite volume and was closed and had a quantization of levels. Now this system is attached to infinite waveguide, so necessarily any quantization will be lost. And we should discuss something else. So what replaces eigenvalues in this case? Useful objects, which in some sense replace it, basically their poles can be considered as the poles of scattering matrix in the complex plane. And in this Heidelberg approach, they are just complex zeros of this deformed Hamiltonian. Deformation is of rank of finite rank, and this depends on how many propagating channels one can send this particle. Because in simple situation it's just single channel, but it may be several, and it's interesting to consider several. So I plagiarized this figure from Frederick Klopp, one very nice article about resonances, because it shows what happened. So before we had eigenvalues on the real axis. Now the envelopes of them are resonances which lie in below real axis. They are complex and they have imaginary parts. And imaginary parts, by quantum uncertainty relation, they are related to inverse of this should be related with some times. What are these times? Physicists know what are these times. These are typically times of escape of a particle via this. So if one takes the system, sends a particle there, it lives there some time and goes back. So typical times are associated, or decay times, are associated with inverse resonance widths in moral sense. One can give a more precise description of that. Therefore, imaginary parts are important to understand, and really the only thing I probably will have time to tell, that one can address in the language of nonlinear sigma model the simplest non-trivial quantity, the distribution, the density in the complex plane, or concentrating basically on distribution of appropriately scaled imaginary parts. So appropriately scaled, it means natural to scale them with some typical separation, this delta, typical separation between their real parts in closed system. And this is really the formula that we discovered, that there is one-to-one correspondence under some assumptions, nevertheless, but quite broad assumptions. So if one knows Sembauer order parameter function, one can map it by some differentiation operation and integration, so just straightforward operations. One can map it to this density of resonances, and one can study different cases. One can very easily, okay, this function, this order parameter function in 0 dimensions in situation of 1 grain is very simple. It depends just a simple exponential, and one gets result which is obtained many years ago and several times by different method, and recently was reproduced also by Tanya and Masha. Also was checked experimentally, and probably the last thing, the really new and non-trivial thing is to consider banded matrices deformed by this deformation of the sort I described. And it turns out that fortunately some time ago my collaborator Misha Skvortsov and his friend Pasha Ostrovsky, they calculated in one case, in the case of semi-infinite system, so a system which starts here and descends to infinity. In this case, they calculated explicitly and non-perturbatively Sembauer order parameter function, and using it, one can get explicit distribution of these resonance widths, and to find that it shows 3 different regimes. For smallest gamma, for resonances which are closest to the real axis, one has a tail in this situation inversely proportional to gamma, and one can explain that this reflects total localization. This is basically decay of states which are away from this attached wire to the lengths exceeding localization lengths. Then there is a second regime, a new regime. This regime was anticipated, was not direct, but was anticipated before. This regime it changes exponent to 3/2, and one can show that it describes the particle diffusing inside localization volume towards the boundary, and finally, when it's very close to the boundary, third regime comes. It's basically an immediate ergodic decay into this attached wire, and this it still changes its asymptotics, its square. So there are 3 ways, and numerics more or less supports it. And I finish here. So we set a framework, very clear framework inside this nonlinear sigma model language for studying distribution of scattering resonances in the complex plane for systems with localization effects. So far, we only were able explicitly to treat one-dimensional systems, but we hope to get at least maybe some understanding of what's going on in the vicinity of localization transition in some models, but it's not yet done. Also this framework in which that formula was derived can be and should be adapted to really Schrödinger operator, not to nonlinear sigma model analog of it, but really to Schrödinger operator, at least in one dimension. And some results are available in physical literature due to Kunz-Shapiro paper and a very nice paper by Frederick Klopp, mathematical paper. Frederick claims that some of Kunz-Shapiro results are incorrect. Probably this is correct. But still, I think it was a useful attempt, and one of the first attempts to get on the problem. And I hope to get some further insights beyond that, and I hope beyond Frederick in this approach. Thank you.
Thank you, Jan, for a very nice talk. Are there any questions or comments?
So in the localized phase, can this be derived without using the sigma model?
It means derived, I don't, okay. Frederick has some rigorous results on density of resonances in some regimes in one-dimensional situation when there is localization. And they more or less, with what I was able to understand, agree with what I know about this distribution. Basically, they more or less reproduce this part of our result.
Oh, that's
Yes. Others seem to be not addressed just in that, but it could be addressed.
The other regimes do not exist, right?
This regime does not, no. This second does not exist, but third exists. I can even show you. Yes, this regime exists when you come.
Oh yeah, you're
yes.
right. You're right. I mean, this is when the localization sensors are very close.
Yes,
to the edge of
closer to mean-free pass.
And but
Yes.
yeah, then
This
it's,
does not
it's
exist.
dark.
It only exists in quasi 1D because it's due to diffusion. So that's my answer to this. Definitely Frederick's approach and also Shapiro approach, they are very different from our look to me. Very different from our approach. It will be very interesting to join them and to see.
It's not very natural to use the sigma model and the localization regime since its derivation somehow assumed. Okay. at least
No,
from the-
in banded case, it's perfectly okay. So these results which I show, they are for banded case. Moreover, okay, as a physicist, I cannot beat numerics done by my collaborators. You see, when we increase the size, because our results are expected to be valid when this system tends to infinity, we see how with increasing size it approaches this theoretical curve. Really, they approach it. So no doubt, okay, no reasonable doubt that these are correct formulas. So yes, you are right. That okay, but this is interesting philosophical question. Yes, indeed, you assume a weak disorder limit when you derive the linear sigma model, but when you put it already this model in the lattice, it has phase transition in it. Of course, it's how to say. But you know, physicists say that good model works much beyond its original way of derivation because it grasps some universal phenomena. Of course, you are formally right, but morally, I think it's still correct point of
The
view.
question was just, I thought that we understand Anderson localization so well that such phenomenon should have a simple description.
Okay, I can, you see, if you just say the following, if you just say the words without calculation, that you put a particle, it diffuses to the boundary, and then escapes immediately, you get this prediction. Sorry. From these words, you get 3/2. But it turns out, okay, now my fellow physicists say, why this long calculation explicit if we know that it should be the case? But this calculation shows that it's in fact, in some sense, wrong thinking. If you have the same idea will be if you have a single channel wire. Okay, let me just, if you have a quasi one-dimensional sample, but attached to it just a single waveguide with single mode, then you still can give the same argument. It diffuses, hits it, and escapes, and you should have the same result. No. One can show that this is wrong. In order to have it, one needs to have parameter number of channels really big, otherwise you do not have this regime. So this calculation shows that this is naive logic. It has some truth in it, but it's naive.
Further questions? Yeah.
I have a, sorry, can you go to the first slide?
Yes.
You mentioned at the beginning that the simplest case for physicists is when random potential is delta-correlated.
Delta correlated, yes. That's what I put here.
So in that practice, it corresponds to the case of white holes, right?
Yes,
So, but the operator itself is not well defined.
absolutely. That's why I say that physicists like it. But physicists like to work with things which are not well defined. Only there you can find something interesting. But okay, to be honest, the following thing. You consider really replace it with some exponentially decaying thing with a finite radius, which is perfectly well defined, and make this calculation. In the end, you may send this radius to 0 and see that your quantities, for example, this alpha, not here, but here, this parameter alpha, which stems from this will be tending to finite limit.
So for the physicist, how is this simpler than other cases? So
Why it's simpler? Why it's simpler to work with white noise? I don't know, technically simpler. I cannot say. You see, it's usually if something has a finite range of correlation, it's more difficult to write equations for it. For example, if you do, I don't know, something like transfer metrics, it's nice to have something on very short correlated from one step to the other, then you can make approximation. Yes.
Because when you do the step, the third from the bottom line, right? I mean,
Yeah.
you go from the computation expectation. This is just compute an integral, right? From
Yes.
Gaussian variables.
Absolutely.
And if the Gaussian variables are zero correlated, the integral is just simpler to compute.
Yes, yes.
That's-
It's technical answer, yes.
But it's not the technical answer. This is what's happening.
That's
real life. I mean,
that's why people like it.
mathematicians, I mean,
I agree with you 100%.
no difference between two people.
But maybe it's interesting mathematical question how really to define this regularization procedure. So because making it finite radius is clearly just a regularization procedure. Why in the end after regularization it remains finite? It's an interesting question to be answered.
At least with the case without magnetic field, this has been done by many people, including
Okay,
higher level.
great to know.
Further questions, comments?
Oh, well, actually, I had a question. In the d-dimensional case, right? Imagine that instead of attaching a single wire, just one channel to infinity,
Yes.
just attach, let's say free diffusion outside the body,
Yes.
right? It does the same nonlinear.
No, because you see, then it can escape from a huge boundary, and then our formula will be invalidated because formula used that you can escape from something which can be mapped on a single Q matrix. It's like you can escape only many possibilities to escape, but only from a single point. In principle, what you ask is interesting question also.
It seems to be the physical, the real physical realization, right? You have a sample.
No.
A finite sample of random material.
I politely disagree. No, what you say is correct. It's not that I disagree with the statement. I disagree that even in experiment, one can realize when it escapes only locally. In fact, I was a part of experiment. You may imagine what I'm experimenting with. But I at least helped to understand the experiment, checking one of these limits when it was really escaped from a point.
Okay.
Okay, if there are no further comments or questions, before we thank Jan again, let me just remind you that we have a lunch at 12:30 downstairs, and if there are any dietary restrictions, that you should communicate them to us in the break. So we will have let's thank Jan